everyone, and welcome to this episode of Dark Chatter. I'm Markus Mosbech, a PhD student at University of Sydney, and with me today is Deanna Hooper. She did her PhD in Aachen, and she has afterwards done a postdoc in Brussels and is now doing another postdoc in Helsinki. Welcome, Deanna.
Yeah, hi, it's great to be here. Thanks for having me. I'm really excited to talk about my new paper with you all.
So we're going to talk about Deanna's new paper about constraining dark matter interactions with neutrinos through Lyman Alpha. And can you tell us a bit about what are the main takeaways from this, Deanna?
Yeah, so in this paper, we've basically been revisiting the scenario of dark matter interacting with massive neutrinos. And this is a scenario that leaves a lot of imprints on structure formation, especially at late times. So for this, we think that Lyman Alpha data will be extremely important to constrain these. So Lyman Alpha data really just allows us to probe late time structure formation. And what we found is that the Lyman Alpha data actually prefer dark matter neutrino interactions over lambda CDM. So we find a 3 sigma preference for non-zero interactions. So we've done an analysis as to what's happening with the flux and why this is the case. But it does really seem that these interacting scenarios can fit the Lyman Alpha flux better than lambda CDM. So that's the key summary of the paper.
Okay, so I know you've used class to do these computations. For those who are uninitiated, can you tell us a bit about what class is, given that you're also one of the main developers?
Yeah, somehow I ended up becoming a main developer. So class is a cosmology code. It's a Boltzmann code. And it allows you to go from an underlying cosmological model to the actual cosmological observables. So class has inbuilt many models, mainly lambda CDM, many extensions to the dark sector, many dark energy models. And you set class up with whatever input parameters you want, whichever model you want. You run it in a few seconds normally or less, and it will calculate, so it will follow the entire background and perturbation history of all of the species. It will follow the entire thermal evolution. And then at the end of the day, it spits out all of the angular power spectra, both the lens and the unlensed versions, and the matter power spectrum. And you can also request class to print out things like all of the thermodynamical quantities, all of the background quantities. So it's basically the code that lets you go, one of the codes that lets you go from your underlying model to the actual observables that we can compare against the data.
Great. Yeah, so this sounds like a very useful tool to have. But given that class works linearly and this Lyman Alpha data is usually in what we call the nonlinear regime, how does this all work together?
Yeah, so this is a super cool question. So as you say, class only deals with linear structure formation. Lyman Alpha data is deeply, deeply nonlinear. Normally, in order to go, so the actual observable you have with Lyman Alpha data is the flux, which is the amount of light you get from a distant quasar after it's traveled through a hydrogen cloud. And normally, in order to do the mapping between a specific flux and a matter power spectrum, you actually need to run a dedicated n-body simulation. So this is where you account for the whole evolution of the hydrogen cloud and everything happening in between. And if you're lucky, these hydro sims take about 3 weeks to run, often longer. So they're quite difficult to use, especially if you want to do MCMCs, where you do a full parameter scan to figure out what are the viable parameter space of your model. If you change any underlying cosmological parameter, you would need to run a new simulation, which of course is unfeasible if you want to do 10,000 or 100,000 steps in an MCMC. So back during my PhD, we came up with an alternative idea where we built a Lyman Alpha likelihood that circumvents the need for these n-body sims. So in fact, if I can just share a slide here, because I think there's an image that will make it a bit clearer. So what we do is we focus on the suppression that any non-cold dark matter model induces on the matter power spectrum. So this suppression we parameterize with the transfer function, which would just give us the ratio between our non-cold dark matter power spectrum and the underlying cold dark matter one. And we parameterize this with alpha, beta, gamma. This was something that was already done in the literature. Now, alpha will give you the overall point in the matter power spectrum where the suppression begins, and beta and gamma control the overall shape of the suppression. So this was initially proposed, this parameterization was proposed in 2017 by Murgi et al. In Trieste. And what we did is we turn this parameterization into a likelihood. So we chose over 100 different benchmark cases of alpha, beta, gamma. For each set of alpha, beta, gamma, we also have a set of cosmological parameters and astrophysical parameters. Now, the astrophysical parameters are things like the temperature of the intergalactic medium. Now, for each one of these benchmark cases, we ran a simulation already. So this allowed, and with the simulation, we could compare to the Lyman Alpha data and obtain the chi-square. So with these 120 benchmark cases that we ran, we were actually able to construct a grid of simulations. So what our likelihood does is it will calculate the alpha, beta, gamma for your cosmological model using class. Then it will use the alpha, beta, gamma, the cosmological parameters, and the astrophysical parameters. And it will do this three-dimensional interpolation within our grid of simulations. So at the end of the day, it spits out the overall chi-square from the Lyman Alpha likelihood for your given model. Now, of course, there are several caveats here. The first one is that it only works on models that can be described by alpha, beta, gamma. So if you have any model that does not fit this shape, we cannot describe it with alpha, beta, gamma. And the likelihood will actually warn you, like, what you're doing doesn't make sense. Then, of course, we need to make sure that we're never extrapolating too far beyond the grid. There's a lot of checks already inbuilt in the likelihood that warn you if you're doing something slightly suspect. But the idea is that any model that can be parameterized by alpha, beta, gamma, our likelihood can deal with them. And we tested this on dark matter, dark radiation interactions back when we released this likelihood. Now in this paper, for the first time, we've actually applied it to the case of massive neutrinos. We did a lot of checks to make sure that it was working for massive neutrinos. And now we've actually been able to use it. So this really does circumvent the need for the hydrosims. So then it takes out the whole nonlinear part because we just do this interpolation for the nonlinear parts.
So it's essentially, it looks at, you have a mapping of what would a linear power spectrum look like in the nonlinear regime because you have done so many nonlinear calculations already. Exactly.
So then we assume that we can interpolate in the nonlinear space based on the ones we've already calculated. And I think the technical takeaway I would give is that remapping bounds from warm dark matter is not a good strategy in a lot of cases. So often, in order to avoid these hydrodynamical simulations, people will take existing bounds from warm dark matter and just apply them to their own model. And I've done this in many papers as well, because for warm dark matter, hydrosims have been run. So it's very easy to just remap onto your model. But if the shape of your suppression differs slightly from warm dark matter, then you cannot do this. And this is one of the things we actually showed, because in the case of dark matter massive neutrinos, the interactions produce a spectrum that is similar to warm dark matter, but not completely similar. And if we had just remapped warm dark matter bounds, we wouldn't have found this preference. And this is something we emphasize in the paper as to why it could be that nobody's found this in the past. It's because often people just remap these bounds. So a bit of a more technical takeaway from the paper is that if you remap existing bounds, you might miss some interplay of parameters that actually allows you to find a preference at the level of the flux.
Super interesting point. So for instance, if I wanted to start using Lyman Alpha, what would be a good place to start?
So I think, honestly, in this case, I would say go to the literature first, because there's a lot of different Lyman Alpha data sets available, and not all of them are good for what you want to do. Like in our case, we used Mike Hyras data. We didn't use XQ100 because our interpolator can't deal with it. We didn't use SDSS because there's no prescription for the nonlinearities for our model. So I think the first thing is to figure out what data set you can actually use in your case. But if you decide, for an example, that you're looking at a model that can be constrained with alpha, beta, gamma, then I would recommend reading the paper where we release alpha, beta, gamma. And then you just download MontePython. MontePython is one of these parameter extraction codes. It has inbuilt now in the public version this alpha, beta, gamma likelihood. There you just check if your model, for an example, warm dark matter, is already encoded in the likelihood. If it is, you just do two runs, one which we call a no data run, which just checks that what you're doing is consistent, and then you can already launch the main data run. If your model is not already in the likelihood, you need to add a few lines of code just so that the likelihood can deal with it. But all models that are in class are also in the likelihood. Well, not all of them, I should say not all of them, but about 10 of the main models that are in class, we already inbuilt into the likelihood. So I think it's just making sure that what you're using is the correct tool for the job at hand. Once you've decided this is the data set you want to use, then I would say just look at the examples, look at what we've done in the past, and then go ahead and use it. Of
So-
course, MontyPython also comes with SDSS data as well, which you can use in different cases, but there you do have to be careful because SDSS does not account for nonlinearities. So if your model is nonlinear, you want to be careful with Lyman Alpha data.
So essentially, if I put a model into class that I come up with, and I find that the suppression is well described by these alpha, beta, gamma parameters, I can just plug and play.
Mostly, you would just need to add a few lines in the likelihood, basically telling it, because there's one step in the likelihood where we need to calculate what we call the lambda CDM equivalent. So that each time with the transfer function, you don't compare to a reference lambda CDM, but you compare to the lambda CDM equivalent of your model. Now, in the case of dark radiation, for an example, this means remapping the dark radiation into other parameters so that your redshift of equality is the same. There's already a few lines for that. In the case of dark matter interactions, for an example, it's just telling class, set the interactions to 0 to calculate the equivalent model. So this is 2 lines. So if your new model has interactions or has any type of thing like this, you just need to tell the likelihood how to calculate the lambda CDM equivalent. And this is usually 2-3 lines. And you can see like 10 example cases, and then you just add the 2 lines, and then it's plug and play.
When doing this work, what for you personally was the most challenging part?
Honestly, I think one of the biggest challenges we had here is that nobody has done this type of analysis before. So there are analyses in the literature for the case of dark matter scattering off of massless neutrinos, and often these use an approximate Lyman alpha likelihood. So, and of course, the case of dark matter massive neutrinos, as you know, has been investigated by yourself and the others in Sydney, but only using Planck and BAO data. So the case of dark matter massive neutrinos using any type of Lyman alpha data that was not an approximate method has not been done before. And of course, our results do show a slight preference. So the first question we have to ask ourselves is, how can we believe our results? And it's quite difficult when you don't have something to compare it to. And I can actually say that we had these results already back in March, and we didn't publish until October. And all of that time between March and October was us cross-checking our own results. So we redid the analysis. I think in the end, we did it about 12 times, using different priors, using different configurations of the likelihood, different configurations of MontyPython, just to make sure that what we were doing was reasonable. And in all of these runs, we consistently found this preference for non-zero interactions. So I think the most challenging part was actually convincing ourselves that what we were doing was reasonable and that what we were doing was actually the correct way of doing things. So I think that was a big challenge, actually. But the good thing is that because of all of the tests we've done, by now we're very confident about our results. Of course, there could be something we've overlooked, but we really feel like we turned over every rock and looked everywhere we could for a bug in the code and a mistake. And at the end, we're like, no, there really is just this preference in the data. So I think it led to the good thing that we're pretty convinced about our results by now.
So that makes me think, maybe you can show us a bit more on the figure. How exactly does the data look? What are we looking at?
Get to it here. So in fact, let me go directly to the flux here. So the flux is the actual observable that we have from Lyman alpha data. And here you can see in black how lambda CDM fits the flux. So every horizontal band that you see here corresponds to a different redshift bin. You see we go from redshift of 4.2 to 5.4. These are just the redshifts that are, so we look at the light coming from distant quasars, and then we bin it in a specific way to have a good redshift and K binning. So you can see that the K binning and the redshift binning is equidistant. So in black here, you can see lambda CDM going through the data points. And especially if you look at the redshifts of 5 and 4.6, you can see that lambda CDM doesn't go through the center of the data points. It goes a bit further down than what you'd hope. Whereas the interacting scenario, which is the interacting dark matter massive neutrinos, which we show here in blue, actually does fit the data slightly better. So here is quite difficult to see by eye, but if you do a chi-square analysis, Lyman alpha data actually gives you a chi-square of -8 for the interacting case, with 1 extra degree of freedom, so that is a 3 sigma preference. The reason is we have this overall tilting of our flux. And we've actually broken this down to analyze what is causing this tilting of the flux. You can see that we have a slight enhancement at large scales and a suppression at small scales. And we broke this down into its 2 main components. So what we do here in the dark green and in the light green curves is we analyze the impact of individual aspects of the model. So in the dark green case, we fix everything to its lambda CDM best fitting parameters, with the exception of the interaction strength. Now here for the interaction strength, we take the best fit from our model, from the MCMC we did with our actual interacting case. So this isolates the impact of the interactions. And you can see that the net effect here is an overall tilting. You have a sharp suppression on small scales and a slight enhancement on small scales. In the light green case, we do something very similar, but where we isolate the impact of the astrophysical or nuisance parameters. So here we fix everything to lambda CDM. We have no interactions, but we use the astrophysical parameters that we obtain from our best fit scenario. The biggest astrophysical parameter at play here is actually the temperature of the intergalactic medium. And here we actually do see that we shift in the other direction. So we get a slight suppression on large scales and an enhancement on small scales. And the combined effect of these is to allow you to have a slight suppression on on large scales on the left of the figure. So you have a slight enhancement on the left of the figure and a slight suppression on the right. This is the net effect of the two. And this is actually enough to resolve the existing tension between Lyman Alpha and CMB data. So it's really this slight tilting that gives us the overall preference for this model. And what this looks like at the level of the MCMC, if we focus just on the panel on the left here. So this is the one-dimensional posterior distribution from our MCMC. So on the left, it's just for the strength of the interaction, this UIDM new parameter, which you can just see at the bottom is just a function of some underlying cross-section and some dark matter mass. And normally when you put a constraint on an interaction strength, what you expect is a Gaussian centered around 0, and the tail of the Gaussian gives you the 2 sigma bound. What you can see here is that our posterior is not centered around 0. In fact, it's centered around a value of like 5.3 in arbitrary units. And this is actually more than 3 sigma away from the 0 value you'd expect in lambda CDM. So we really do have this overall shift, and we know that it's driven by the interplay between the intergalactic medium temperature and the interaction strength.
So I also remember in the paper that you were, given the boldness of the claim of interacting dark matter detected, you were quite hesitant to claim anything definite other than it fits the data better. Do you have any other thoughts on what else it could be?
Yeah, so of course we try to be very cautious. We at some point had actually written, like, depending how you analyze this, it's a 5 sigma preference, and we can't put a 5 sigma preference. We cannot do that. So we calculated it more carefully, taking into account that it is not a perfect Gaussian. And yeah, we try to be rather cautious about the claim we're making. But I think there's 2 main areas that concern us slightly. I wouldn't say we're overly concerned, but they are points that do raise the question of, is there some issue there? Now, one of them is the overall slope of the Lyman alpha flux. There is a parameter that gives you this overall slope of the Lyman alpha flux, which is known as NF, which is highly confusing with the other NF we have in cosmology. But we have this overall slope of the suppression. And our grid for alpha, beta, gamma was constructed for NF between -2.27 and -2.35. It's a very narrow range, but it was extrapolated to work in the range of -2.0 to -2.6. So it should be a broad enough range. Now, our best fitting model here actually gives us an overall NF of -2.5. So it is still within the range where the grid should work, but it is a border case. And this means that it's a case where the alpha, beta, gamma formalism could break down slightly. Now, we think this should be fine because this has been found in other models as well, but we have actually not done yet a dedicated hydrosim for such a low value of NF. So this is an obvious check to do, and I can say that we actually have that hydrosim ongoing. We're just waiting for the cluster to spit out results, where we're running the hydrosim for our best fit model, and we want to see if the flux that we obtain matches the flux predicted by the alpha, beta, gamma likelihood. So this is one check to see if the alpha, beta, gamma likelihood is performing accurately in these regions. We think it should be, but we need the flux to be sure. So that is one thing that made us a bit cautious. And the other thing is, I mentioned here that we have this we have the interplay with the temperature of the intergalactic medium. And in our best fit model, we actually find a temperature that is about 25% lower than the values you can find in the literature. However, all of the values in the literature for this temperature of the intergalactic medium are derived assuming lambda CDM. So it's not completely clear if this is the temperature we would expect in non-lambda CDM scenarios. It's not completely clear if the interacting case would affect the temperature enough to justify this low temperature. So this is also something we have ongoing, is testing just how realistic these temperature values are. We do think it's not too unreasonable because there's nothing that proves this temperature to be wrong. There's no constraint saying you can't have such a low temperature. So we think it should be fine, but this is also something that needs more checking, is where exactly, how valid is this temperature that we found? But I think despite these two caveats, the fact still remains that the Lyman Alpha data prefer non-lambda CDM flux. And even if the flux we found turns out not to be the actual flux that corresponds to our model because alpha, beta, gamma broke down, we still found a flux that fits better than lambda CDM. The question now is, did we find the correct model that gives that flux? If that makes sense.
That makes a lot of sense. Thank you. So if we're going to take a bit of a zoom out and a broader view on the general search for what is dark matter, where do you think this fits in?
So we're quite excited about this paper, to be honest, because apart from the claim of a hint of an interaction, we know that there is a tension between Lyman Alpha data and CMB data. So we know that Lyman Alpha data does not prefer the same values of the lambda CDM parameters that you find with Planck. You can find in the literature cases where this is given the focus of omega m, where there's a 2.5 sigma discrepancy. You can find cases where they focus on NS, where again, you find a 2.5 sigma discrepancy between Lyman Alpha and CMB data. So what we've shown here, especially with the analysis where we show the interplay at the level of the flux, we've shown what a model might need to reconcile these data sets, because we can remap the type of model that we found into a shift of omega m, for an example. We can also remap at the relevant scales. We can remap this into a shift of NS. So we've shown the type of interplay that you need at the level of the flux in order to reconcile these data sets. So even if it turns out that what we claim is not true, even if it turns out that there's not this detection, we have shown the direction that we need to go for what a model needs in order to reconcile these data sets. And we have shown that Lyman Alpha does just prefer a non-lambda CDM flux, and regardless of whether that's the underlying model, I think it's an important step forward in beyond lambda CDM physics, because there are two tensions in the literature that are very well known. There's the H0 tension, the sigma 8 tension, and they get a lot of attention. But I think this discrepancy between Lyman Alpha and CMB data doesn't get the attention it deserves. And it could be a place that has strong hints for beyond lambda CDM physics. So I'm hoping that on the one hand, this is just a reminder to people that this is a tension worth considering. And on the other hand, it will help with the idea of what a model needs in order to reconcile these data sets. So I do think it fits quite nicely in the broader picture of dark matter searches.
That's some very good points. I think that exhausts my lines of questioning. Do you have anything you would like to add?
I think one thing I've learned about this is that writing a 4-page paper is ridiculously difficult, because we kept it to 4 pages. We could easily have written a 20-page
I appreciate
paper.
that. It was very nice to read.
Thank you. I do also want to mention here something that we don't have a lot of space to go into detail in the paper, that we've also redone this analysis for the case of massless neutrinos, and we actually find the same preference, but shifted by about 30%, so 30% lower, which is actually what you expect if you compare at the level of the matter power spectrum, the impact of massive versus massless interacting neutrinos. You basically get an overall shift of 30%. And then doing the MCMC, we do find a non-zero preference also in the massless case. And this was super interesting to us because this is a case that has been done before in the literature, but always using the approximate remapping of warm dark matter bounds, which is what gives us that key takeaway that I said before. Because when you remap warm dark matter bounds for the case of massless neutrinos, you don't get this preference. And the fact that we found the preference with the peak shifted by 30%, which matches what we have at the level of the matter power spectrum, was actually a very good test for us and kind of a good proof that what we're doing seems to be correct, because we found an expected result in the case of the massless case. So Lyman Alpha data do prefer interactions, but it doesn't necessarily have to be with massive neutrinos. It could also be with massless neutrinos. And this is something that we easily could have written another 4 pages on, but we just slipped it in. It is in the paper, but it's mentioned briefly. But I do think that's also a very key part of our analysis, because to me, it solidifies that what we're doing is on the right track.
Yeah, I think that's a very good point, that it's important to check that what you're doing actually works, and that
Yes.
you're not what you're applying is applicable to your situation.
Yeah. And if I can make another comment, so in this paper we use alpha beta gamma, which is a pretty robust likelihood if your model can be described by alpha beta gamma. But there's a lot of models that cannot be described by alpha beta gamma. These are models that, for an example, where you have a fraction of interacting dark matter. In those cases, you might have a plateau instead of a net 100% suppression. When that is the case, alpha beta gamma fails. So I do want to briefly advertise alpha beta gamma delta. We like going through the Greek alphabets. Alpha beta gamma delta is the extension to alpha beta gamma, where we've got a new parameter that allows us to account for plateaus in the suppression. To do this, we've built a whole new grid. I think by now we have over 200 new simulations in the grid, plus the alpha beta gamma ones. This new likelihood is expected to be able to cover so many more models. We've already got results for dark matter baryon interactions. They're not yet published. We have ongoing results for 3 other models. And it's actually very likely that in early next year, January, February next year, we're going to make this new alpha beta gamma delta likelihood public, which will allow us to do the analysis we've done for dark matter neutrino interactions to many other dark matter interacting scenarios. And it will be very interesting to see if the Lyman Alpha data actually find hints for other interactions as well, now that we can do the full analysis for pretty much any non-cold dark matter model. So I'm pretty excited about that, and we really do hope to release that in January next year. So I just wanted to advertise that, because it's been a lot of work, but I'm super keen to get that one out.
Exciting times for doing nonlinear predictions with linear physics.
Exactly, for getting away with not doing nonlinear physics.
Yeah, we've got you doing it already for us. But yeah.